and welcome. The main focus of this video will be on the binomial probability distribution. If you are not yet familiar with the basic concepts of probability, I suggest you first watch my video series on the fundamentals of probability before proceeding with watching this video. The link to the first part of that video series is provided in the description below. Now, before we get into the meat of this topic, let us first do a quick review of variables. So a variable is typically a characteristic of interest in a study. Very common examples are age, sex, disease status. Now, as the word itself suggests, its value varies from individual to individual at a given point in time. Like, for instance, if we randomly selected a sample of, say, 10 subjects from a particular population, this sample will more likely than not have individuals with different ages, and we will have a particular frequency distribution of male and female. Now, there will also be variables whose values vary within the same individual at different points in time. A person's random blood sugar levels, for instance, varies a lot all throughout the day. If someone gets sick, for instance, with the common cold and recovers from it a week later, the disease status then and now is clearly different. Now, this variation generally results from the inherent biologic variations among individuals. Now, measurement errors can also contribute to this variation. Now, variables can either be qualitative or quantitative. Now, qualitative variables are variables whose categories are simply used as labels to distinguish one group from another. So we have here as examples sex, which is either male or female, disease status, like does a particular individual have disease or not. Now, place of residence could also be another example. One could use city names as categories. Now, often numerical representation of the categories are used. Like, for instance, disease status of 0 would mean that the patient does not have the disease. Disease status of 1, on the other hand, would mean that the patient has the disease. The majority of times, such representations are merely for labeling or coding and not for comparison. Now, quantitative variables, on the other hand, have values that indicate a quantity or amount. Now, these values can be expressed numerically and can be arranged according to magnitude. Now, frequent examples are age, height, weight, and blood pressure. Now, one important thing about quantitative variables is that they may either be discrete or continuous. Discrete variables can assume only integral values or whole numbers, like the number of children in a particular family or number of beds in a particular hospital. Now, this is in contrast to continuous variables, which can attain any value, and that includes fractions or decimals. So a good way of regarding these two types of quantitative variables is that discrete data can be counted, while continuous data is measured using an instrument. Discrete data contains distinct or separate values, while continuous data includes any value within range. Discrete data is tabulated in what's called a frequency distribution, with each entry containing the count of their occurrences. Now, here's an example of a frequency distribution taken from a 2014 New England Journal of Medicine article entitled Very Early Administration of Progesterone for Acute Traumatic Brain Injury. The variable of interest here is the cause of injury, and each row under this column heading are that variable's different categories. The numbers that you see in some of the cells are counts of the occurrences of each category. Now, we've worked with tables such as this before in previous videos where we were computing for the different probabilities of various events or outcomes. Just as counts of discrete categories can be summarized in frequency distributions, values of a random variable can also be summarized in a special kind of distribution called a probability distribution. Now, unlike your ordinary frequency distribution, each value of a variable, be it discrete or continuous, is linked to a particular probability instead of a count or frequency. So, going back to the table from the previous slide, we see that the total number of patients whose cause of traumatic brain injury was a motor vehicular accident is 322. Now, computing for the marginal probability, we get 0.365. So this particular category of the variable cause of injury has that probability linked to it. Now, a probability distribution is basically a description of a random phenomenon, which is expressed in terms of the probabilities of events. While a table or a graph can be used to describe a probability distribution, now certain statistical applications can derive an equation that can adequately describe a particular probability distribution. Now, such equation can then be used to calculate the probability of interest. Now, in other situations, a theoretical probability distribution provides a good fit to the distribution of the variable of interest. Now, here are some useful theoretical probability distributions in medicine. The binomial distribution I will be talking about in this video, while the Poisson and the normal distributions I will be tackling in a subsequent video. Now, without further ado, let's begin learning about the binomial distribution. As the word binomial suggests, there are only two mutually exclusive outcomes of interest. Now, would a particular patient be dead or alive at the end of a particular follow-up period? Now, would a patient remain sick or get well after being treated with an investigational drug? While being maintained on immune modulators, would a lupus patient go into a flare or stay in remission? Now, would a baby be born full term or premature? Now, all these situations feature only two possible outcomes. Now, each experiment or trial that has a dichotomous outcome of interest is called a Bernoulli trial. Now, a sequence of such trials is called a Bernoulli process, and this is where we can derive our binomial distribution. Now, here are a few important prerequisites about the Bernoulli process. Now, each Bernoulli trial results in only one of two possible mutually exclusive outcomes. We often describe these outcomes as either a success or a failure. Success in this sense actually means being successful in getting the outcome, whether that outcome may be good or bad, while failure means one has failed to attain the outcome of interest. Next, in a Bernoulli process, the probability of a success should remain constant from trial to trial, and each trial should also be independent from each other. Whichever outcome a trial will get should not in any way be dependent on preceding trials, nor should that particular trial influence the outcome of subsequent trials. Now, these are all conditions one has to assume when dealing with binomial distributions. These are basically the conditions we look for in a particular situation or experiment to see if modeling it using a binomial distribution would be appropriate or not. We will be going back to these assumptions again in a bit. Now, let's consider this 2000 New England Journal of Medicine article. A bit of a background to this paper first. Traditionally, mechanical ventilation tidal volumes were set at 10 to 15 milliliters kilogram body weight. So a 70 kilogram person would be given tidal volumes of 700 to 1050 milliliters per breath, which carries a substantial risk of stretch-induced lung injury, particularly in patients being ventilated for acute respiratory distress syndrome or ARDS. This study basically showed that lower tidal volumes, that is, 6 milliliters per kilogram body weight, or rather ideal body weight, resulted in improved mortality compared to traditional tidal volumes. Now, here's Table 4 of that study, which shows its main outcome variables. Let us focus our attention first on the first main outcome, which is death before a patient was discharged home and was breathing without assistance. Now, take note that death here is regarded as the success event. So if we were to randomly select a patient who was randomly assigned to the low tidal volume group, that patient's probability of dying is 0.31, as opposed to 0.398 in the traditional tidal volume group. Now, in real-life practice, this joint probability of 0.31 is an estimate of the probability of dying in a patient with ARDS requiring mechanical ventilation if he or she was ventilated with 6 milliliters per kilogram of tidal volume. Now, before we proceed, let us first assess if we could model this piece of data using the binomial probability distribution. We can easily summarize the assumptions of the binomial distribution using the mnemonic BINS. Now, first question is the outcome of interest binary or dichotomous? In our example, the patient either dies or survives by the end of the study period, which was 180 days, or until the patient was discharged. So the answer to this question is yes. Next question, are the individual trials independent? So after satisfying the study's inclusion criteria, Each patient was then randomized to receive either traditional tidal volumes or low tidal volumes. So it should be true that one patient is independent of the other patient. So the answer to this question is also yes. Next, is a sample size, that is the number of trials fixed? Now, in clinical trials, sample sizes are determined in advance. In this study, 861 patients with ARDS requiring mechanical ventilation were included, with 432 patients treated with low tidal volume ventilation, all of whom were followed until the end of 180 days or until the patient was discharged. So we can assume that the N is fixed. Lastly, we should have fixed P, or a fixed probability of death in this case, for each patient in the sample. In the low tidal volume arm, the probability of death was determined at 0.31, and this probability applies to all the patients included in that particular group. So therefore, our answer to this last question is also yes. From here, we segue into the underlying assumptions for the binomial distribution. So first, the outcome of interest has to be dichotomous or binary, meaning having only two outcomes, namely a success and a failure. Next, each trial has to be independent, which means that the outcome of one trial should not be affected by the outcome of another trial. There should be a fixed number of these independent trials, and the probability of success, or the probability of attaining the outcome of interest, should be constant for all the n number of trials. Now, going back to our example, the outcome of death in this case is considered as the success, while if a patient survives, then it's considered a failure of attaining the outcome of interest, that is, which is death. Now, let's say we randomly selected 5 ARDS patients from the low tidal volume group. What then would be the probability that exactly 3 of these 5 patients will die? As determined by this study, the joint probability of death among those ARDS patients treated with low tidal volume ventilation is 0.31. Since we're dealing with a dichotomous variable with mutually exclusive events, the probability of survival then would be the complement of the probability of death. Now, suppose the random selection resulted in this kind of sequence. So we have a success, then a failure, then a success, then another success, then a failure. Since each patient is independent of each other, the probability of the above sequence of outcomes is found by means of the multiplication rule, which is such. So computing for this probability, we get 0.0142. We are, however, not interested in the order of occurrence of death and survival, but instead the probability of the occurrence of exactly 3 deaths out of 5 randomly selected patients. Moreover, there are 10 different ways in which these 5 patients could be selected basing on their outcomes. And each of these sequences has the same probability of occurring. Now, what then would be the probability of the occurrence of exactly 3 deaths out of 5 randomly selected patients, considering there are 10 ways in which the random selection can occur? We multiply the number 10 to the probability of 0.0142 we got from earlier. So, our desired probability then would be 0.1419. Now, it would be all good and well to individually write down the possible ways or sequences in which a small sample of patients can be drawn. But what if the sample is large? Well, we could still make use of the same process, but this now becomes a very tedious task. An easier technique is to make use of the combination formula to determine the possible number of sequences or ways in which a particular sample can be drawn from a larger group. Now, take note of the factorial here, symbolized by an exclamation point. A factorial is defined as the product of an integer and all the positive integers below it. So 5 factorial will be 5 times 4 times 3 times 2 times 1, and 3 factorial will be 3 times 2 times 1. So the combination of 5 taken 3 is equal to 10, which are the 10 possible ways in which 5 patients, with 3 of them dying, can be randomly drawn. Now, take note of the combination formula here, so it can also be written as such, and this is read as n taken x. So, if x is a random variable that represents the number of successes in n number of trials, the probability of x outcomes in a group of size n, if each outcome has probability p and is independent from all other outcomes, is given by this. So let's apply this formula to the example. Our n is equal to 5, our x, or the number of successes, is equal to 3, the probability of success, or death in this case, is 0.31, and its complement is 0.69. So plugging in the values, we get the same probability of 0.1419. Now, what if we considered values of x, or the number of successes, other than 3? Let's refer to this table here. The first column shows the possible values for x given an n that's equal to 5. The middle three columns, on the other hand, show the values for the different terms in the binomial distribution equation, and the last column gives us the resultant probability for each value of x. Now, if we're to graph all these resultant probabilities in a vertical bar graph, we get something like this. Now, if we're to smoothen this graph, we won't get a symmetrical bell-shaped curve that you'd expect from normal distribution, which we'll be taking up in a subsequent video. Now, take note that this is the binomial probability distribution for n equals 5 and p equals 0.31. What is interesting about the binomial distribution is that we can have different plots or shapes for the curve depending on what values for n and p we have. Now, in this figure here, we have three binomial distributions, each of which having the same value for n, which is 20, but different values for p, as you can see in the legend box. Notice how these distributions change in shape, height, width, and position with increasing values for p. In this figure here, on the other hand, we have again three binomial distributions, each with the same value for p, which is 0.5, but this time with increasing values for n, as you can see in the legend box. Again, notice how these distributions change in shape, height, width, and position with increasing values for n. Now, in a binomial distribution, the n and p are what are called its parameters. So if you know the values for n and p, that should be enough to specify a binomial distribution. Now, as we just learned a while ago, each possible combination of n and p gives us a different binomial distribution. Now, each of these distributions has its own respective mean, variance, and standard deviation. I'll be talking about the measures of central tendency and variance in a subsequent video. Now, the formula for the mean of a binomial distribution would be this, while the formulas for the variance and standard deviation would be these. Note that the standard deviation is simply the square root of the variance. Now, another important thing to know about binomial distribution is that if the n is large enough, with a p that's close to 0.5, then the random variable x would approximate a normal distribution. We will be discussing about the concept of approximation when I talk about the normal distribution in a subsequent video. Just to give you a glimpse of what happens in normal approximation, let's go back to this image here. Now, take note of how the curve of the binomial distribution smoothens to resemble a symmetrical bell-shaped curve as you increase the size of n. Hopefully, you still remember what the three axioms of probability are. Now, let's see if the binomial distribution satisfies these requirements. Let's go back to this table. Let's pay attention to the values under the last column. As was mentioned earlier, these are the resultant probabilities for each real value of x, which are in this case from 0 to 5. Note that all of them are non-negative and are between 0 and 1, so that satisfies the first axiom. Now, if we sum up all the resultant probabilities, we get a total of 1. This, in effect, satisfies the second axiom. Now, notice that in all rows, we have the same values for n, which is 5, and p, which is 0.31. The only value that changes each time is the value of x, which varies from 0 to 5. Now, clearly, x cannot be, for example, 3 and 4 at the same time. So with that, we can treat each row as an occurrence that is mutually exclusive as far as the other rows are concerned. And each mutually exclusive row is represented by the respective resultant probability. So overall, third axiom is also satisfied. Still with this table, let's do a few more exercises. From earlier, we already determined that with a random selection of 5 ARDS patients treated with low tidal volumes, the probability that 3 of them will die is 0.142. Now, what if we want to know the probability that of these 5 randomly selected patients, less than 3 of them will die? If we say x is less than 3, x here would either mean 2 or 1 or 0. If we want to know the probability that x is less than 3, we simply add the resultant probabilities of x equal to 2, x equal to 1, and x equal to 0. So we get a total probability of 0.823. Now, what if we want to know the probability that at most 3 will die? This time, we include the resultant probability if x is equal to 3 in the sum, like so. So we get the total probability of 0.965. Now, what if we want to know the probability that more than 3 patients will die? Well, we do the same thing as earlier, but this time adding the resultant probabilities when x equal to 4 and x equal to 5. So we get the probability of 0.035. But again, what if the sample size is large? Then clearly, computing for each resultant probability becomes really tedious. It's a good thing, however, that we have cumulative binomial probability distribution tables. Now, these are tables that give us all the computed cumulative, so take note, cumulative probabilities beginning with x equal to 0 up to some specific number of successes given a particular value for n and p. Now, here's a screenshot of such table which I got from the textbook by Daniel and Cross. Now, since our n is equal to 5, we focus on this part of the distribution table. So we want to know what the probability that x is equal to 3 is. Now from earlier, we already computed it to be 0.1419, but what if we want to use the table instead to find out this probability? Now if we look at this part of the table, where x is equal to 3 and p is equal to 0.31 intersect, we see 0.9653, which is way different from 0.1419 that we got earlier. Now keep in mind though that this is a table of cumulative probabilities. So in this case, 0.9653 is the sum of the resultant probabilities from x is equal to 0 up to x is equal to 3. So in order to know what the probability that x is equal to 3 is, we subtract the cumulative probability up to x equal to 2 from the cumulative probability up to x equal to 3. We then get 0.1419. So the trivial difference here from 0.1418 is because of the rounding off. Now, what if we want to know the probability that x is more than 3? If we look here in the table where x is equal to 3, we note the cumulative probability of 0.9653. We are, however, interested in the probability that x is more than 3, not including 3, that is if x is 4 and above. We already know that the sum of all probabilities in a given binomial distribution is 1. So, thinking of x equal to 3 as a cutoff point, we simply subtract the cumulative probability up to x equal to 3, that is 0.9653, from the total probability, which is 1. We then get 0.0347, which we can round off to 0.035, and get the same value from the computed one that we did a few slides ago.